So I think we can start. So I'm Samuel. I'm from LIP at Portugal, and I'm here to introduce you to this initiative, which is a joint webinar series of the BigHPC project and the UT Austin Portugal Program. I'd like to start to issue a thank you for participating in this session. In this webinar, we will welcome João Barbosa from MAC to talk about software-defined scientific visualization. So today our speaker is João Barbosa, that joined the Texas Advanced Computing Center Scalable Visualization team in 2011 as a graduate research assistant while pursuing a dual PhD doctor at the University of Texas at Austin and the Portuguese MAPI program in high performance graphics under the UT Austin Portugal Program. As a full-time research associate at TAC, João has worked in several scientific visualization projects ranging from high-level applications such as gas and oil to low-level high-performance software packages in partnership with leading hardware and software companies. His current research focus is high-performance real-time in-situ photorealistic ray tracing. He also moved back to Portugal last year and settled in Braga to join the Minho Advanced Computing Center, MAC, as a full-time researcher in scientific visualization. I will be the moderator of this session, and from my side, I'm graduated in Lisbon University with a degree of computer science engineering, and I'm now finishing my master's degree dissertation. So let's just do here some briefing of the management of our session. So I'd like to inform you that you can and should interact during the presentation, but for that, you should use the Q&A button to share your questions. During the presentation, there will be no discussion moments, but at the end of the webinar, we will provide some minutes to discuss all the questions and interact directly with you. I will be also monitoring the Q&A activity, and I ensure all questions are dealt by the speaker at the right time. So just remember that you should keep your microphone muted during the session to avoid the noise. The session will be recorded and you will have access to it in the end. When the discussion starts at the end of the presentation, and if you want to share your questions, please click the raise hand so I can give you the word. So now let's move on to the presentation. So I will kindly ask João, I will stop my share here and I will ask João to start his sharing. Just stop here.
So much, Samuel. Let me see if I can pull this over. Is it sharing?
Yes, João.
Thank you so much. Oh, well, thank you so much. And thank you to the organization for inviting me for this talk. I'll be talking about software-defined visualization, a little bit of the history behind it. What are the basic ideas that led us to develop software-defined visualization? What are the new challenges? Where are we going? So that's the basic idea that I want to give you on this presentation. I'm not going to go into too many technical details. I'm not going to talk about really elaborate visualization techniques, just a little bit of an history of where we've been and where we're going. Most of this presentation is going to be based on some slides from TAC, specifically Paul Navratil, which was my previous manager. I was there for a really long time. So most of the work that I've done is actually related to tech. So they were kind enough to give me permission to use some of the slide decks that I used before. So this presentation is going to be a lot based on what tech and what I did at tech, more than Mac, because it's been such a short time in Portugal that we are just starting. So let's talk about scientific visualization. It's one of the cornerstones of BigHPC today. When we're talking about computing, we're basically talking about three major areas. The simulation part of the code, where we want to use our mathematical models from any domain and create a facsimile of the reality, digital twin, if you wish, of the reality, and explore new techniques and new methodologies to study things from drug discovery to the universe. And based on that, we actually need to have analytics so that we can look into what the data is giving us and creating visualizations out of it and seeing with our own eyes what is happening on the data. But sometimes it's also not enough. So new techniques as machine learning are coming up to explore and allow us to make queries to the data, to the numerical data itself. But as having said, the purpose of computing is insight, and it's not numbers. What I want to say with this, or what I was expressing, is basically this idea. And here I'm using a well-known quartet of data, the Amscombe data set. And if we look at it, it's just a bunch of numbers that we cannot get an idea out of it. And if we use statistic analysis on it, the values that we get for each one of the data sets are completely, are exactly the same. So if we calculate mean, variance, covariance, they are exactly the same. Even the regression, linear regression that we get out of the data is exactly the same. So if we were analyzing this data from a purely perspective numerical methods, what we would conclude is that the data sets are exactly the same, or they are extremely similar. But once we do visualization, and here using probably the most used visualization tool in the world, which is Excel, if we actually plot the data, we'll see that they have completely different behavior. So the idea of visualization, specifically scientific visualization, is to actually look into these large numeric data sets and get insight out of the data itself, using something that we've used for millennia, which is our visual cortex, to recognize patterns, see behavior, and so forth. Okay, so again, the idea is those were really simple examples, but we can extrapolate to more complex examples. And what we want to do with scientific visualization is actually have an accurate representation, either in 2D or 3D space, of what our simulation has produced. What are the quantities, what are the values and the properties that we're looking at. So the idea is to be able to produce these really nice images that allow us to recognize patterns and recognize situations more quickly than just browsing through the data. Okay, so here's some examples of what data and what kind of visualizations we can get out of it. This is actually a volume data set out of a turbulent flow. And what we want to do is be able to visualize large concentrations of flow, large concentrations of particles, and be able to project some of the properties of that flow into the visualization itself. That's what gives us insight. That's what gives us a knowledge of what the data is actually, how the simulation is actually behaving. This is something that it's been done since the advent of computing. We've always wanted to do that, and we wanted to do that with the most accurate and possible representation that we can. We cannot avoid the scientific method, meaning we need to reproduce data, we need to do it every single time. Here's just another cool image from a colleague of mine from TAC, Greg Foss. It represents the magnetosphere of a star. So in scientific visualization, we most of the time allows us to see things that were not possible. Even if we did a physical experiment, we would not be possible to see properties mapped into the data that we're looking at. Or in this case, the case of a star, it's impossible to reproduce in reality. So there's no physical experiment that can do that so that we can observe. And then again, we are always talking about terabytes of data on these data sets. Okay, just another cool example of an earthquake. This was a simulation done by the UT Austin at ICES, which is a group dedicated specifically to Earth observation and so forth. They created a really nice model of the earthquake of Japan a couple of years ago, actually more than a decade ago, in 2011. And visualization allows us to take that model and see how the waves actually propagated through the globe. So that's things that we want to do. That's what scientific visualization allows us to do. And the other thing that scientific visualization allows us to do is to see detail at large scales, especially when we use tile displays. In this case, Rattler from TAC with a 9 screen tile display, each one projecting a 4K image. And we're seeing details of a fluid flow from a direct numeric simulation that would be impossible to see in a really small screen. So we also want to be able to see things in large detail and with a lot of context, which these types of screens allows us to do. So why do we need software-defined visualization? Weren't we okay with what we had before? And the answer is not really. So what we had before was this notion that we had this HPC system where we would run our simulation, we would write all our time steps that we wanted, and we would put them on a data archive within our remote site in our HPC center. And then when we wanted to actually analyze the data and visualize it, we would bring it to a local resource, our computer, and we would use some techniques, some software to actually explore the data and see what is in there. So that's all fine and dandy, especially if we have this really small data set. Our raw data, if it is extremely small, we can easily do that. We can easily use our local machine to produce geometry and then render pixels to see the, the science that we want to see. So that's not a big deal. But what happens when our data is actually extremely large? How do we handle that data? How are we able to transfer all that information to it? Do we simply gather the data and send it over the network to our remote machine to visualize? What are our constraints? So, and here the problem becomes, how long can we wait for the data? And this is a really important question, because bringing the data from our data center into our local station for analysis depends very much on the type of technology that we're looking at. So for instance, here's 3 examples of really common links, commercial links on the internet with 10 gigabytes to 54 megabits. And here are some data sizes of data sets that we typically work with. And again, if we're talking about small data sizes on the scale of 1 gigabit, well, we could probably wait 2.5 minutes to get the data on a typical home connection and process the data afterwards. But data is actually growing. The data sets are getting to the scale of a terabyte. And today there's data sets that actually getting to the scale of 1 petabyte. And with 1 petabyte, even if we have a 10 gigabyte connection, it actually takes 12 days to migrate the data from one point to the other. So there's got to be another solution that we can work with. Well, the primary solution, what we did beginning of the 2000s, early 2010s, what we did was to migrate the resource into the data center. And we would create these clusters, HPC clusters, solely dedicated to visualization and visualization resources. It works fine. Again, it's a solution. The only thing that we need to send into our display are just the pixels. So it's basically the same thing as sending in a stream of video. So it's not that bad. It does take advantage of the fact that it's within the network of the data center. So at least 10 gigabytes should be available there for us to access the data. That's fine. It does allow us to use techniques when we have these large data sets in distributed memory models, typical of HPC clusters, where we can, for instance, use each one of our nodes within the large visualization HPC cluster to load a portion of the data, generate the geometry, and then one of the nodes gathers and renders our science. Or if we want to be smarter, we can actually produce a partial of the image within each one of my nodes on the cluster, and then use techniques like depth compositing to actually produce the final image on the screen. So all of these became available on the data center, but they all depend on the fact that it's a post hoc approach, meaning I'll run my simulation. The simulation will still write all the checkpointing into disk, and then the cluster and the visualization cluster will load the data, run the appropriate algorithms, and generate the image. So there's still some kind of a bottleneck in there. And problems with this post hoc visualization approach is that it's highly dependent, at least it was until the 2010s, highly dependent on GPU visualization. So we would use GPUs mainly to generate and rasterize the image, the data that we wanted to generate the final image. The other problem, even if we create this large cluster, is that we are actually dedicating a huge amount of resources solely for visualization. Either a separate cluster or a portion of the cluster will be dedicated only to visualization, which is kind of a waste of resources. Because if no one is actually doing analysis, the resources will be just there idling for something to do. And they are not actually being used for computing, which is the main goal of any HPC data center, is to provide computing into it. And still we suffer from the large data set transfers. As data gets bigger, as we go into the terabyte and the petabyte ranges, we still need to do these large transfers, either to a remote location, our PC at home, or even within the data center itself into another cluster. So we still suffer with that idea. So the idea of in-situ visualization kind of arose to deal with some of the issues that we're seeing on the visualization world. Processors are growing. The number of available processors is actually being exponentially almost in every data center. If we look at the HPC top 500 list, we'll see that systems are almost always changing positions with every release of the list. So the resources are becoming available. Not only that, but they are enabling us to tackle larger and larger problems from the visualization point of view. We are definitely doing larger and larger simulations with larger and larger number of nodes and resources within the HPC system. The other problem is that file systems as they are not scaling up at the same rate as the processor technology, this CPU, GPU technology is evolving, which is creating this huge gap between simulation, visualization, and storage. So we need to somehow address that, and the post visualization, the post-hoc still depends too much on that bottleneck. We are touching disk every time that we need to save time steps or doing analysis when we need to do it that. And the idea of in-situ visualization was created to kind of mitigate that by taking advantage of the fact that by placing the simulation and the visualization on the same machine and running simultaneously, we can directly access the application's memory and get the data out and do our analysis as we need to do this, the final product. And in the end, this allows us to, one, do analysis online, meaning know exactly what's happening in the simulation at each time, and do a little bit of computational steering. Most of the numeric models, some of them are unstable. So sometimes we need to tweak parameters during simulation. The simulation completely blows up in the middle, and we're talking about really large simulations. So simulations that take days, weeks to compute. And if it fails on the first couple of hours, we might as well just terminate the simulation and restart it again. So this is the idea of computational steering. And in that sense, in-situ analysis and in-situ visualization more specifically allows us to actually see what's going on during simulation. And this changes the model. So now we don't have these dedicated resources, either our local machine or the HPC system, but we are actually using the same system for simulation and visualization. This creates a problem. So before, since we were too dependent on GPUs, we could only run visualization workloads on nodes that had GPU. So we had to come up with some idea of extending that data, extending that model, and enabling visualization to actually run within the simulation system. It's the only way that we can actually place the two of them working together. And not all systems, especially tech back then, most of its technology was based on Intel x86 architectures. Only a small fraction at accelerators from NVIDIA and other vendors. So if we want to do this tight coupling between simulation and visualization, we need a solution that it's based on software and not so much on the hardware side. So the idea was that things would, the machines in the future would be many core processors, either by having multiple cores within the same chip or GPU capable devices. So that allowed us to use a couple of new techniques into visualization that did not depend on hardware specific solutions. We could easily tackle the AVX extensions from CPUs. The idea is that the whole stack of the software-defined visualization was going to be optimized for each one of the processors and the process family that the HPC cluster would have. And still, the idea behind this type of technology was to get out of a tightly coupled solution that we had, which was dependent on GPUs, which is rasterization, and enable new techniques, visualization techniques to be useful, like ray tracing, and allow the visualization and the simulation analysis to run on the same machine. So we wanted to tackle the problem of having to dump into disk and do a post-hoc visualization platform on it. So what we depended on, the technique that was behind most of the visualizations before software-defined rasterization was rasterization, which is basically taking our data and just projecting it into a 2D plane. The idea is to take the geometry, and it's extremely dependent on being able to generate geometry and projecting that geometry to generate an image. So there are some limitations of what we can do with that technique. Ray tracing was around for a really long time. It is used in graphics since the early 70s, 80s. It's been producing better and better images. It's the basis for the film industry and the animation industry today. So using that for visualization at its appeals. One, it would be extremely efficient on many core technologies, Intel, NVIDIA's, AMD's, whatever. It would be able to perform more complex functions on data visualization, not just generate geometry, but be able to sample the data as we went through it. And the other aspect is that we could do physically based shading easily on these types of visualizations, right? What that makes it interesting is that this is early work, early 2012, 2013 work out of tech with the University of Florida, where we took some of their data, some rock samples that were digitalized using CAT scans, and where we simulated a fluid flow through the rock core, and then generated some streamlines that gives us an indication of where the water is flowing, how fast it's flowing, and so forth. And what we're looking at is early results of comparing the traditional technique using rasterization with some data and using some ray tracing approach. And what you can see from the two images is that it actually, it's easier to read the data on the image on the right. It's easier to have a depth perception and understand where exactly the flows are happening within the core sample. On the left side, that information kind of gets lost due to the light conditions of a traditional rasterizer technique. So beyond attacking the problem of the data movement within the system, we also ended up, the technique also ended up providing new ways of looking at the data and more detailed ways of doing it the data, still using physically based techniques for our understanding. Of course, that the primary goal is actually to scale up, and these are, well, one of them is the same core sample, but with a lot more detail. It's a more fine-grained detail. It's a really large data set. And we were able to render it using ray tracing techniques, mainly from Intel, with Embry and Osprey was one of the early adopters of software-defined visualization. And we were able to get that data vivid and give a really nice presentation of the data itself. On the right side there, it's a model of ocean currents within the pole, the North Pole actually. The data set is absolutely massive. There was some doubts if we were able to render the data set with details, and these type of techniques or this early work show that it would be possible to do it using a volume rendering technique and using these tightly coupled in situ's case to generate the final images that we wanted to analyze. This is some of the latest work out of TAC and Intel. My apologies. It should play. And the idea here is that we can now use these massive data sets within the HPC system. In this case, it's using actually from Taro, which is TAC's latest and greatest machine. And specifically, they're obtain nodes to be able to scale up the simulation and the visualization simultaneously. So I don't know exactly why this video is not playing, but the idea is that we can do the simulation, really large simulations and visualizations at the same time. So what is the current status specifically for in situ? From the simulation developer, implementing visualization with things like ParaView and Catalyst, or Visit LibSim allows you to do these type of techniques. They've incorporated most of what was known from software-defined visualization to explore the in-situs and in-loco cases, and it's able to do that. It is possible to integrate with tools like Adios or libraries like Adios that, in fact, intersect the data from the simulation. If we have some old simulation code, we might want to intersect the data either from memory or what we call in transit when it's being sent over the network to other nodes. So when the nodes are communicating, capture that data and render the visualization. Or even today, you can go directly to do rendering calls if you feel lucky and you want to do low-level optimizations and use Intel Ospreys or optics from NVIDIA or some other vendor. From the simulation user perspective, well, either the developer has incorporated any of the above techniques, or it's going to be really tough to do it on your own. But you can still do it specifically with Adios, and you can intersect the data and create your own pipeline that you can use to generate this visualization. Okay, and the other option is, well, I hope that the technology actually still makes postdoc analysis viable, and that means breaking up the bottleneck of the I/O between the HPC system, the storage, and our visualization system. So what is coming next? Well, machines are still growing. They are becoming heterogeneous in nature more and more. The latest top 500s, the machines that are on top are actually completely heterogeneous machines where you have CPUs and GPUs within the machine itself. So that's a challenge that we need to solve. The memory hierarchy is actually getting deeper. We are getting more levels of caching, staging, and so forth. That was something that was discussed a couple of webinars ago. I'm not going to go into detail a minute, but it is a challenge that we need to address. And we're getting layers of I/O on top of layers of I/O. We're using hot and cold storages where we want to be fast for some reasons and where we want to store things for later analysis. So all of that is coming to play. And all of that is a challenge that we need to address with exascale computing. So is there a solution for that right now? And there's a lot of potential solutions. There's a lot of technology out there, a lot of research being done to address these problems. But in the end, there's challenges of analyzing really large data sets. And the problems are just compounding because if you talk with researchers, they want to go more accurate, larger data sets, more detail, more cell sizes. The simulation world is actually exploding. The amount of data that we're looking at is exploding. And so is the hardware. The hardware is becoming more elaborate, is becoming faster, but it's also more complex and more difficult to actually fine tune and find something that is consistent on long runs. So one of the problems is technology is changing so fast that sometimes what we produced yesterday is not exactly suitable for the next generation that it's coming tomorrow. Having said that, there's some projects that give me some hope. One of them is actually Anari. Anari went into the software defined visualization, took some of the experiments and some of the ideas that were explored by each one of the vendors independently. And now it's looking to actually make a common platform and a common API that allows us to bring them all together. The idea is that in the future, we will not need to program for a specific vendor. We'll have our visualization applications. We'll have this layer of Anari in between that will target correctly whatever is the hardware underneath our machine, either CPUs, GPUs, or whatever new technology comes next. So all that mapping will happen, and this comes from software-defined visualization, specifically for the fact that most of the application vendors actually liked the idea and started incorporating it into their pipelines and into their applications and engines, and that forced specifically vendors to come up with some way of creating a uniform API for the technology. And the other idea is that more and more consortiums are coming up. Solar ray tracing consortium is one of them. The idea is to now go beyond visualization. So until now, we were worried about, the community itself was worried about how to scale up these visualization techniques, how to bring them closer to the simulation. How could we do tightly coupled integrations? How that would be feasible, and how we would get it to interactive setting with the user, allow it to manipulate data and create new visualizations on the fly. And now it's going beyond that. It's looking into how do we actually integrate correctly visualization and simulation, and can we use some of the techniques that we use on the visualization into the simulation world? Can we use these engines to actually accelerate some of that? And it's also coming around the ray tracing for science. How do we define specific forms of surfaces, volumes, particles? Because every single vendor, every single researcher actually defines things on their own. So they're trying to come up with a standard to unify all of these APIs and all of these concepts around something that everyone in the community can agree. This is just an example of what is in the pipeline, right? This is an application out of the University of Aveiro. It's something that I've been working in the past, where we are integrating all the lessons that we learned. So we are doing in-situ visualization onto the application itself to be able to control, manipulate the simulation. But we're also embedding, getting a little back from the visualization. So one of the problems that this simulation had was that it needed to calculate particle collisions with buildings and do some really nice physics around those collisions to determine paths. So the application itself is simulating pollutant concentration within an urban area. And that depends on a fluid flow that it's computed from CFD, and then a dispersion code that tries to calculate where particles accumulate and what are the high areas of concentration on a 3D space within the urban mesh. And around these particle building collisions and vegetation collisions, there's some physics around it. And the way that they were doing it before was using these technique of marching the particles through the grid. And we actually went in and changed the visualization. We changed the algorithm so that we would use the ray tracer visualization. So there's a tightly coupled simulation visualization case where the simulation produces the results and the visualization offers a ray tracing engine to compute the collisions to the simulation. So it's really tightly coupled and produces really good results. In fact, on the specific case, the calculation went from 3 hours to 3 minutes each time step. So it was a huge benefit for the application itself. So these are the goals of in-situ visualization, specifically when we take into account software-defined visualization techniques. In-situ has become the de facto visualization technique for large-scale simulations and large-scale analysis. It's impossible to handle these massive data sets without considering in-situ visualization, unless we want to wait a really long time for data to get into places that we need it. The other idea and software-defined visualization techniques definitely allowed us to go in and make these visualizations from in-situ actually work in conjunction with simulation. It's also addressing the need and the problem that arose from heterogeneity, and it's arising the mix of CPUs and GPUs, specifically with the new initiative from Manari. So it's actually helping help define that, and it's moving that target forward with time. And the community that was created around software-defined visualization is actually growing. It's looking ahead and looking into other aspects of this tightly coupled situation, where it's not looking only at the fact at the need to extract data and create the visualizations for analysis or for computational steering, but also looking at ways of actually providing to the simulation tools and libraries that they can use to improve their simulation. And having said that, thank you so much for your attention. I'm open for questions. I think I was able to keep the time.
Thank you very much, John, for your very nice presentation. I'm looking here to the Q&A, and we still not have any questions for now. I'm also looking to any raised hand. So please, if you have any questions, just raise your hand or write them on Q&A. So maybe I start with the first question now, between the time anyone places some question. João, you told about the complexity of the computation and the simulation and the visualizations, and also the challenge for data. And my question is about the problem now of the exascale computing. So we are scaling all the data sets and also the capability of the computation. And there is also the requirement for the visualization that I suppose is outside, well, on the simple computer size in terms of hardware, right? So in the end, we need to send all these computations to the supercomputers and then have all that detailed visualization back. And as I understood for your examples, this kind of visualization turns to be always more detailed with more realism and bigger, right? So what is the kind of challenge that you have now fulfilling that requirement?
So there's a couple of challenges, right? The exascale challenge is something that we still don't know how to meet. We can scale up to the current sizes that we have now on HPC systems, meaning we can do a visualization with 10,000 nodes. That shouldn't be a problem. But we are always struggling with two things. One is, how do we efficiently integrate into simulation? How do we efficiently mitigate the problem of the I/O bottleneck, right? For instance, there's techniques today that will do, for instance, they will write into this temporary storage, high-efficient storage, a time step so that the visualization can go in and fetch it. That's not an ideal case. So the question is, how do we effectively integrate into the visualization? And the other question is, and this is the holy grail today, is how do we do it without overstretching the simulation? How do we do it without overstretching the time of the simulation? The most common technique is, I'll do a simulation step, I'll dump the data, intercept it somewhere, create my visualization, and then allow the simulation to continue. So this is one way of doing it. The other way is, and this way, what it does is it automatically increments the size, the time that it takes for the simulation to run, because you're running both on the same resources. So there's no way of extending those two. And they run on a sequential way. So simulation, visualization, simulation, visualization. The other way is, well, we allocate more resources and we intersect the data, move it to the other resource and do the visualization separately so that the simulation can continue. Moving the data goes into the I/O bottleneck. We need to move the data somehow. And we are going to lose either time for the data to move, or we're going to lose precision, because we need to compress the data somehow. And compression will always lead to loss of information in order to do the visualization. So the holy grail now is, and there's a couple of techniques that are coming up to do that, is how do we connect simulation and visualization in such a way that we can explore the idle time of the simulation to actually do the viz? How do we minimize the viz impact into the simulation? So that's one of the challenges that is now. The other challenge is, and here Anari is coming into play and probably helping a little bit, although the first version is still away from what ideally we wanted. How do we handle the fact that we have a CPU, a generic CPU on the machine, and a GPU on the machine as well? Today, both of them can actually perform these operations for both simulation and visualization. So how do we schedule these workloads within the machine to be able to get into the next step? Does that make sense?
Yes, João, thank you for your explanation. We have also here another question in the Q&A. So Ricardo Macedo asked imagine that for some use cases, we want to see things with great detail. And in this case, we may need lots of data and computation time. But for others, we could have a more simple representation that validates our points and therefore use less resources. So my question is, how exact should these visualizations be? Are the models for representing these visualizations static, or do they have some degree of configurability to deal with different granularities?
There's techniques to handle different granularities, right? For instance, AMR is one of them, adaptive mesh refinement, which can be applied to a lot of stuff, where we can basically say, I don't want that much detail on this part, but I'm really interested on these little cluster here. So I'm refining my mesh on a particular spot on a particular part of the data and kind of blurring out the rest. So that's something that it's traditional in simulation, and visualization is now able to do in some scenarios. The other side of the coin is we can actually also embed this into the visualization pipeline as well. I'm remembering a visualization that I did a couple of years ago, where we had this data set that represented gas concentration on a particular part of space. It was a cluster cloud simulation, and the gas itself had a different resolution than certain stars within the environment. That is also possible to do. It's trickier, but it's possible to do.
Thank you, João. It seems we don't have any more questions on the Q&A. I ask again the audience if anyone wants to place a question, please raise your hand if you have any question. Okay, so people are very shy today, it seems. Well, João, maybe you can stop sharing your slide. Thank you. I'll start again here from my side. So let me just change it again. So last opportunity to make your question, please. Just do it. If you have any missing question now. So, okay, I think we can finish this webinar. Thank you very much again, João, for your presentation and all the knowledge you share with us about these thematics. And so With this, we end this series of webinars, and we will promote soon the next series of webinars. Hope during next month it will be announced. And thank you again, everyone, for your time and to be here, and see you next time.